Well, hello everyone. Welcome to the first lecture for Intro to Geology, GL 101, here at Grand Rapids Community College. And this is a hybrid course, so the lectures will be recorded like this, and you watch them asynchronous, which means on your own time. And then when we meet for labs, I'm assuming that you've already watched each of these lectures. And so when it comes time to do lab, you have the necessary background on the material to complete the lab successfully. My name is Eric, and I'm your instructor for this semester, and this is going to be fun. So in this lecture, we're going to basically cover all the topics very quickly of what we're going to be going over during the semester. And so you'll get a little taste of kind of each little subject. I've got about a slide or two on each one, and then we'll kind of wrap up talking about plate tectonics, which will be the first major topic that we cover next. So there'll be a little bit of plate tectonics in lab. So I want to give you just a little bit of background on that. But first, let's talk about geology in general. So geology is a multidisciplinary science, and it is also referred to as earth science. And as such, it incorporates lots of different disciplines, other scientific disciplines, into its framework, and therefore we call it a multidisciplinary science or an applied science. Okay, so you see here we have chemistry. So that deals with the composition or chemical composition, I guess, of the Earth's materials, and the composition of the atmosphere, which is the air surrounding the Earth, and the hydrosphere, which is water on the surface and underground. Also, we incorporate physics, so the physical properties and behaviors of those earth materials, like how do they react with one another, what happens when you deform them, things like that. And overall, a larger picture in physics is the Earth's place within the universe. So that would be planetary geology and the like. And that's studying other planets, other moons in our solar system is kind of where we're at now. And then it incorporates biology, so understanding ancient life and how that life evolved, and the impact that life has on geologic processes and the impact that geologic processes has on life. And then there's an engineering standpoint, so technology, designing for disasters and sustainability. And this includes earth materials, earth resources, mineral energy resources, that sort of thing, but also in construction. Oftentimes a road crew or someone building a house or someone building any other kind of structure would consult with geologists to find out what are the materials below that site and what types of things might we be able to build in different areas. So geology is a science that pursues an understanding of the Earth in two broad categories. Physical geology, which are the Earth materials like rocks and minerals, and also hydrocarbons, things like that. Processes, so how do those different materials form? How do they interact with one another, particularly when we're talking about plate tectonics and that sort of thing. And then the other broad category, and this would be the second class you would take if you're a geology major, is historical geology. And that's the origin of the Earth and the origin of life and the evolution of the Earth and life, okay? So you are in physical geology now, that's this class, and we do touch on the origin of the planet a little bit, we do touch on the evolution a little bit and biology, but primarily in this class what we're concerned with are geologic materials and geologic processes. So why is the study of geology important? Well, it's important because we get a lot of resources from the Earth, and we are affected by the Earth processes, particularly in the event of natural hazards. So for resources, we have mineral resources. That would be iron, gold, nickel, silica, things like that. We have energy, so anything that we get from hydrocarbons, hydrothermal, um, nuclear power, all of that. Geology is very much involved in all of that. So looking for those materials, extracting those materials from the ground, and water. So a lot of people don't realize, but if you are a hydrologist, you are a geologist, so, sometimes called hydrogeologists. And so water is part of the Earth system, okay? It's an Earth material. And water shapes our lives in countless ways, and I'm sure I don't have to tell you that, living here in Michigan. So we study water, and if you were a geologist here in the Midwest, that's primarily what you would study, is water, and what you would do as a profession. For natural hazards, we have earthquakes, volcanoes, floods, and landslides. These are all geologic processes, and they are hazards because we like to build cities and habitate near the places where these things can happen. Mostly because we need water and things like that, or we might need energy, or we might want to live in California because it's nice there, except there's major fault lines that run through it. So all of these things become hazards once people are near them. Okay, so I want you to keep that in mind. And the study of geology is more critical now than ever because of an increasing population. And I want you to think about why that might be. And we'll talk about that a little bit in lab. So population, currently we're at about 7.9 billion. That's of 2021. And you can see down here, we're expected to reach 8 billion by 2023. We may have done that by now. I'm not sure. This is kind of an older slide, a couple years old now, but you can see that from about 1,000 years ago until basically the late 1800s, early 1900s, everything was pretty steady. Population growth wasn't happening very quickly at all over those 1,000 years. And then we see kind of it skyrocketing here in the 1900s and 2000s. And by 2050, it's expected to reach about 9.4 billion people. So with an increasing population, we need resources, right? Supply and demand. People are going to need to use resources. Again, that's going to have increased hazards because there's more people populating the surface of the planet. So they're going to find themselves closer and closer to major geologic centers where things like volcanoes and earthquakes can occur. And so with more people means more people surrounding places that could harm both infrastructure, but also has health risks and even fatal risks in many instances. And also people have a huge environmental impact. And I don't think that's a huge surprise to anybody. But as we impact the environment, we impact the geology of the planet as well. And that can sometimes be a cycle that continues. So some important concepts that we're going to cover that I think I want to introduce now, just to kind of get you thinking about this. We have the Earth system, right? So that's the Earth itself, so rocks, the solid parts of the Earth. We have life, right? The biosphere, so that's human life, animal life, plant life, bacterial life. You've got water, and that's in its liquid form, but also ice. So as a geologist, you would also study glaciers, and we study glaciers. And that's surface water as well. It's just in a different state. It's not liquid, it's solid. But glaciers are very, very important to the evolution of the Earth, particularly the surface of the Earth. And here in Michigan, we are chock full of glacial features, glacial sediment, the effects of glaciation over the last million years or so. Then the air, that's atmosphere. So then we also have the Earth's internal structure, and the Earth is heterogeneous. What that means is made of different things. Hetero means different, geneous means origin, so different origin or different components. And so the Earth's internal structure is made of different things, and that's expressed on the surface. That's how we know that. So we'll talk about that a little bit. We got the rock cycle, so there's rocks everywhere, right? And rocks cycle very similar to the water cycle. We'll talk about both of those things. Then we have geologic time, so human time, right? Which we think of usually in spans of tens to 100 years, versus geologic time, which we usually think of in millions and billions of years. And the Earth is dynamic, like I said, and so it's constantly evolving and reforming and recycling itself, mainly through the process we call plate tectonics. And again, that'll be the next thing that we cover. Here's the Earth system there. So this is just kind of a picture that illustrates what I just mentioned. So you've got the atmosphere, you've got water, and you can see this water here is eroding this sediment and transporting this sediment. So very important. We're going to talk a lot about that in this class. Then you have the solid Earth materials. So we think of that as land, but that's actually going down into the crust of the Earth, and then below the crust into the mantle, and then the core. All of that would be kind of the Earth system or the geosphere. And then you've got life, right? So Earth systems and cycles. So normally if we were in a in-person setting, we would this is where I would sort of ask you questions, but I want you to kind of just think about the Earth, think about the systems I just talked about, and think about what are some of the different components of each of those systems, okay? What types of things would be present in the hydrosphere, right? That's water. So what kind of things happen in the water cycle, okay? And I guess a good clue here, a good hint to think about is maybe the process of evaporation or the process of precipitation or groundwater moving through and minerals dissolved in groundwater, things like that. And then there's cross-cutting concepts. So I want you to think also, how do these things interact with one another? How do the different systems interact? And again, like I said, the Earth's internal structure is heterogeneous. So the basic simple version is the structure of the Earth can be broken down into these 4 different components. You've got the inner core, which is a solid nickel and iron core, about 1,216 kilometers thick. And by the way, in this class, we will be using the metric system primarily. That's kind of the universal for science, regardless of what nation you're in or what culture you're in. We use kilometers instead of miles, and you'll have a chance in lab to practice converting between these two things. There is a bit of math involved in this course, but nothing too advanced, and I'll talk more about that in lab. But anyway, then we also have the outer core, so that's a molten iron and nickel core, and it's molten, so that means it's liquid, okay? Or some kind of fluid, right? Even if it's very thick, it's not solid, it does flow. And it's extremely dense, and it's about 2,270 kilometers thick. Then we have the mantle, which is a rocky shell that extends about 2,900 kilometers away from the core. It's partially molten, right? Not entirely molten, but partially melted. And it convects, and we'll talk about this in lab, but I want you to think about a lava lamp, what a lava lamp is doing if you've ever seen one of those. Maybe your parents were hippies, maybe you were a hippie, and you have a lava lamp around. So I'll talk about that in lab a little bit, but the idea there is that material is being heated up closer to that little light bulb at the bottom of the lava lamp, similar to the way material is heated up near the core. Because it's warmer, it's less dense, because things that are heated up tend to expand, so they're less dense. And so that rises up through the material, which would be the liquid part of the lava lamp. And then as it rises up, it starts to cool, it gets heavy, and then it falls back down, and that cycle repeats. Well, the mantle does the exact same thing. And then also we have the crust, which is this kind of thin, you can think of it like an eggshell. If the Earth were an egg, the crust would be about as thick as the shell of an egg. And it's ranging in thickness from about 3 to 70 kilometers. That's about 40 miles thick. And to scale this, again, atmosphere is 14 to 15 kilometers thick, crust about 10 to 70, mantle 2,900, outer core 2,300, inner core 1,200. And here's, if we took the Earth and we opened it up and looked at the different pieces here, there's the solid inner core, here's the molten outer core, here's the mantle that convects, here's the crust, and then this would be the atmosphere or the surface. Okay. So I encourage you to click on this link in the slides. I post the slides on Blackboard, the naked slides here without any audio on them, so that you can click on links or use them to study, that sort of thing. So go ahead and click on that, but we're going to talk briefly about the Earth's internal structure and how the Earth was formed. So the Earth was formed through a process called accretion. So this is when particles in space have some amount of gravity, no matter how big or small they are. And so they pull on other things. And when the gravity of two different particles are interacting, those two particles come together. If you do this over a long enough time period, I'm talking about billions of years here, eventually everything starts to collide in and form larger and larger masses, body masses, and so that's how we call that process accretion, and that's how we think our planet originally formed, and all the different materials that were out here floating around became incorporated into the Earth. Okay, and that's why we have iron and gold and carbon and silica and oxygen and that sort of thing. Then also we have the rock cycle. So there are 3 different rock types you might remember from high school or middle school or even grade school, or maybe you've just heard about this before, but we have igneous rocks. So those are rocks that are crystallized from magma, and so we call those crystalline rocks. And that can be magma that erupts or magma that slowly cools within the crust, and those are 2 different types of igneous rocks that we'll talk about in this class. Then you have sedimentary rocks. These are lithified, so that means became rock. Fragments, or they're formed from chemical or biological action, and we call these fragmental or clastic rocks. And as the name implies, these are when sediments get compiled together to form a rock. And sediments you can think of like sand or gravel or mud or silt, and even organic materials like fossils. And then we have metamorphic rocks. So these are rocks that have been physically or chemically altered in the solid state. So they didn't completely melt as they were being heated up and pressurized. If they had completely melted, they would just become magma again. And then when they cooled, they'd be an igneous rock. But if they stayed pretty much solid and just kind of deformed plastically or got altered plastically, that's how we get a metamorphic rock, and we would say that rock is foliated. Although there are non-foliated metamorphic rocks. There's a couple we're going to learn about in this class, so keep that in mind. And these 3 different rocks, different rock types are shown here. And I'm not going to give away the goat here and tell you which one's which, but I want you to kind of look at this and see if on your own you can kind of guess which one is an igneous rock, which one is a sedimentary rock, and which one is a metamorphic rock. And how do those things fit into the rock cycle? Okay, and when I introduce the rock cycle on the next slide, I want you to see if you can match the rocks on this slide to the rocks in the next slide. So here's the rock cycle. I like to start down here in the bottom left because I think of everything coming from a magma first, as the planet was molten at one time, billions of years ago. And so the first rocks that would have formed would have been igneous rocks. So I kind of start there in my brain. So you have igneous rocks here that form from magma upwelling up through the crust from the mantle. And they either cool down here or they are into what we call a pluton, more on that later, or they would erupt onto the surface as volcanoes, and we call those volcanic rocks. Both are igneous, all right? And then they cool and solidify, right? And that's the crystallization part. Then they start to weather, right? The atmosphere, water, air starts to interact with these rocks that are on the surface, and it breaks them down, right? That's a weathering process, is the breakdown of rock. And then it gets transported, usually by water, but also by wind and glaciers, and it gets deposited as sediment. That sediment builds up over time, right? And as that happens, we get cementation. So stuff moves in between the small, it moves into, pardon me, the small spaces in between the fragments of rock and cements it together. And then as that stuff gets buried and buried by more and more sediment, it becomes lithified. So it compacts and it hardens into rock. And that's when we have sedimentary rocks. Now, at that point, you can get sedimentary rocks that get exposed to the surface, become sediment again, and the process starts over. So sedimentary rocks can become other sedimentary rocks. Otherwise, if they get buried deep enough, they can be altered or metamorphosed through different tectonic forces. And that applies heat and pressure to the rocks, whether they be igneous rocks, sedimentary rocks, or other metamorphic rocks. And that heating and that pressurizing causes these rocks to begin to alter. If that process runs away to the point where that stuff gets melted, then it would cool again as an igneous rock. Otherwise, it can be exposed to the surface and get weathered and become a sedimentary rock. And so you can see here that the rock cycle is circular, but there's ways that certain things can jump from one step to the other. You can have a sedimentary rock that becomes a metamorphic rock that becomes sediment, and then becomes a sedimentary rock. You have igneous rocks that could, before they get weathered or exposed to the surface, they're still igneous rocks and they can get deformed into metamorphic rocks as well. And so based on what I just explained and thinking about the different rock types, the 3 different rock types that we had in the previous slides, where on Earth do we think these different rock types form? So for sedimentary rocks, because they have to interact with the atmosphere and with water, they form on, drum roll, the surface, okay? And so you're going to get sedimentary rocks that form on the continents, and you're going to get sedimentary rocks that form in the ocean, right? And this is the weathering of oceanic crust and continental crust, and then the transport and deposition of those sediments, generally into the ocean or some sort of body of water. But on the surface, on the dry surface, on the continental surfaces, we also get sedimentary rocks that form, excuse me. And then for igneous rocks, where do we suppose those are going to be? Well, we tend to find them sourced from the mantle, and then the upper part of the mantle, lower part of the crust, in a portion that we call the lithosphere, okay? We get that same, those same locations are also where we see metamorphic rocks forming, okay? And this is usually when mantle product rises up through the mantle, goes into the crust, and then slowly cools or erupts. That's igneous rocks. For metamorphic rocks, we have to have some kind of heat and pressure, so burial or contact with some kind of heat source like magma, or some kind of deformation or plate tectonics. That's what gives us metamorphic rocks. So we'll talk a little bit more about that. Notice no rocks that we know of are forming in the core, and that's because we don't really have any interaction with the core at all, okay? We only know anything about the core because of seismic or earthquake data. But no rocks or materials, generally speaking, make it up through the mantle from the inner or outer core up to us that we know of. The fourth concept that we are going to discuss that's important is geologic time. So the birth of geology and geologic time. So early on, they thought that the Earth was formed from catastrophism, so back-to-back natural disasters. Then a guy named James Hutton came along and introduced something called the law of uniformitarianism. And that's that the physical, chemical, and biological laws that operate today also operated in the past. So rather than there just being a time before now when the Earth was very different and there were just back-to-back natural disasters, crazy stuff happening, he came along and said, no, it's actually the processes that are happening today have always been happening at basically the rate they're happening now. And so what you really need is a lot of time for the Earth to form and for the different structures and materials that we find on the Earth to form. And that started a long process, really only over the last couple hundred years, that we really started to think about just how old the Earth is and just how long Earth processes have been taking place. So let's think about some of these timescales. So if we use we use 1 year as a kind of standard, right? At 10 to the negative 8 years, which is the scale of seconds, that's 0.00000001 years. That's a second. We'd see something like a breath, right, over in the column on the left there. That takes about a second. When it comes to minutes, we would think about a test, how long it takes to take a test would be in minutes. For months, we would think about a semester. For years, we would think about the age of the iPhone, let's say, or something like that. It wouldn't necessarily be proper to talk about it in decades because it's only a decade or so old. Then we have decades, so that would be a human life. So 9 decades, 80 or 90 years. Then you've got a monarchy, so those can last centuries. Even though it seems like Queen Elizabeth lasted for centuries, she's actually part of a long line of rulers that are related to her. So that's one monarchy, so one dynasty, so that lasts about centuries. A country can last as long as a millennia, so that's 1,000 years. And like think Greece or Italy or China or Egypt, they've been around for thousands of years. The United States, not so much, but a quarter of 1,000 years or so. Then you have a volcano, that's in millions of years, so that's 10 to the 6 years. So that's a 1 with 6 zeros after it, so that's a million. We call that an epoch. And then you have continents, and some of the continents, namely North America, parts of Africa, parts of Europe, parts of South America, Australia. These are measured in eons or billions of years, and that's a 1 with 9 zeros after it, so 10 to the 9th. And the way we date the Earth and date rocks is relative age dating and something called absolute age dating. And for relative age dating, this doesn't give us an actual age. This just gives us how old are rocks relative to other rocks that they interact with. So here we've got this dark colored rock here, and these people are at the beach enjoying a not so beautiful sunny day. Or beautiful not so sunny day, I suppose. Anyway, so they're sitting here on this black rock here. And if we look at this outcrop over here, we see a lighter colored rock, and we see fragments of that lighter colored rock sitting down here that have been eroded and weathered away, and theoretically the tide is pulling those down here. And so if this were all buried, right, under lots of other rock and it was exposed at an outcrop and we were able to see fragments of lighter colored rock in darker colored rock, and then above that we have the lighter colored rock that was the source of those fragments, that tells us that the lighter colored rock here is younger than the darker colored rock, based both on the fact that there are fragments of this rock in this black rock here, but also that the lighter rock is just on top of the black rock, right? The darker colored rock. And so we don't know, if this happened 1 million years or 1 billion years ago, but what we do know is that the lighter colored rock here is younger than the darker, and that's called relative age dating. And some relative age dating methods that we use, and we'll get more into this with a lab later on in the semester. We have the law of superposition, so that's when younger layers are on top of older layers, just like in the last slide. We've got the law of cross-cutting relationships. That's when you have something that cuts through another rock. So you have rock cutting through here. So this is a darker basaltic, kind of magnesium and iron-rich volcanic rock cutting through this sedimentary rock, it looks like. So the sedimentary rock in this case would be older because it fractured at some point, or something happened where this darker colored volcanic rock was able to move through it. So the darker material here is younger than the reddish material because the darker material needed the red material to cut into, right? If that red material wasn't there, how could this have cut through? So we call that cross-cutting relationships. And then we also have the law of fossil succession. So that's basically the time scale or chronology of life, and particularly the way life evolves, is usually from simple life to more complex life, right? Think about a bacteria and then think about your golden retriever. Your golden retriever is a lot more complex than a bacteria. So we found clumps of bacteria fossilized in a rock. We would know that that's an older rock than, heaven forbid, a rock with your beautiful little puppy's bones in it. Sorry about that. So then you've got dating methods. So the absolute age dating, we do that in the laboratory. So this is when we're actually getting actual numbers for the ages of things. And we'll talk more about this in the chapter on geologic time, but this is done through measuring the decay of certain elements and the ratio of those elements versus the products they decay into. And when we do this, because things decay at a given rate, we know how much decay has happened, and so we know how old that is. And we've used that to actually date the age of the Earth to about 4.6 billion years old. And that's based on some rocks that we found here on the Earth, but mostly it's based on asteroids and meteors that we've sampled that were formed about the same time as the Earth and have been unaffected since, and we're able to measure isotopes within those rocks and estimate the age of the Earth basically that way. When we're doing geologic cross sections, which we have a whole lab on later in the semester, this is where we would use relative age dating techniques to tell a story about a cross section. So a cross section here just means, imagine like a piece of cake. If I cut a piece of cake and it was a layered cake, and I put it on a plate, and you looked at the side of the piece I gave you, we call that a cross section, right? And so this is a cross section of the Earth, or a cartoon version of one anyway. And based on the methods I mentioned earlier, you'll be able to tell me what formed first, what formed second, what formed third, what formed last, etc. Okay? And you'll be able to tell me what kinds of processes were happening for those things to form or be deposited. Okay? So based on relative and absolute age dates, we are able to come up with the geologic timescale. And these are this timescale bounded by basically epic sort of large geologic events and biological events. And over here we see a pretty common figure for that. And one thing to keep in mind is these kind of time scales over here on the left part of the figure are not to scale. If we look over here on the right, we see that the Precambrian here, which takes up only a small portion at the bottom of this, is actually this big large chunk here. And then all of this colorful stuff with lots of information about the different types of life that were dominant during these periods, that takes up this little portion up here. And that large portion is known as the Precambrian. It happened before the Cambrian era. That is when life exploded. So before that, and I don't mean life literally exploded, I mean the complexity and the various forms of life became very different very quickly. Okay, and so you had kind of an explosion of different body types, different tissue types, things like that, and that happened. And then we have basically fossils from that time increasing in complexity. Before that, there was life, sure, there was bacterial life mostly. In fact, probably that's all there was. Um, and the reason the Precambrian uh, is as large as it is because we don't have a lot of fossils from that time at all. So we don't really break it up into many different parts based on the life that we see. We just call it all the Precambrian, although it does have its own subdivisions, basically. And we do have a lot of rocks exposed on the surface from the Precambrian time. In fact, there's some up in the UP. So then after the Cambrian, or from the beginning of the Cambrian, I should say, on until the present day, that's no longer Precambrian. Now we call that the Phanerozoic. That means revealed life in Greek, and that makes up the remaining 12% of Earth's history. And that's everything from the evolution of fish to flowering plants to dinosaurs to your golden retriever, and that's the time that we have a lot of fossil record from. So we're able to break that up into more pieces, and we have a lot more information about that time period and are able to say more about it. And the Phanerozoic is broken up into three time periods: the Paleozoic, which means oldest life, the Mesozoic, which means middle life, and the Cenozoic, which means most recent life. And again, like I said, the time scale over here is broken up by major geologic events and the fossil record. And so when you have something like the Grand Canyon over here on the right, you can look at each one of these layers and you can find fossils in there. You can see different sediment types. You can see events when there was lots of volcanism, or events when there was lots, maybe a meteorite impact or something like that. That gets preserved in the rock record. And if you have a place like the Grand Canyon, then you can actually tell stories about the time scales based on the sediment records that you see exposed there, okay? And a large portion of the Phanerozoic is preserved there in the Grand Canyon. And we observe it in other parts of the world as well, but the Grand Canyon's a nice one-stop shop for a lot of that kind of stuff. So those were kind of the main concepts that we want to kind of have as a foundation when we're talking about geology. Geologic time, Earth processes, kind of the dynamics of the different parts of the Earth and how they interact with the atmosphere and with life and with water. That's basically all the things that we're going to explore in the class. And when we do this as scientists, we use the scientific method, okay? And since we're going to be talking about plate tectonics next, I'll use plate tectonics as an example of the scientific method, okay? Because it's a fairly recent theory. It's only been around, it's only been an accepted theory for about 60 years or so, 50 years. It's been proposed many times in the past, but the consensus in the scientific community didn't really rally around the theory of plate tectonics until the 1960s. So in order to arrive at the theory of plate tectonics, and it is a theory, just like the theory of evolution, even the theory of gravity, and we get to those through, again, the scientific method, and that's through these different steps here. So we've got observation, then so that's observing something in nature or observing some kind of phenomenon. Interpreting that phenomenon, right? So seeing that something's happening, interpreting the thing that's happening, explaining the thing that's happening, so explanations, and then forming a hypothesis about why it's happening, and then testing that experiment, or testing it through experimentation, testing the hypothesis, and then if all those steps go well and your hypothesis is confirmed and it survives repeated tests, then it becomes a theory. So what is an observation? So an observation is the data, okay? So that's the information gathered with our senses, right? Eyes, ears, nose, mouth, hands, whatever. And an observation that is judged to be valid, so is it a thing you're actually seeing, we would call that data. So then there's an interpretation. What's the cause of the data? And that's a simple description that gives a suggested mechanism that supports the data, right? So what's an explanation? Well, if you have several interpretations that fit together, right, several of these, then you get an explanation. And a scientific explanation can also be a hypothesis, right? So a hypothesis is the same as an explanation in the fact that you see some data, you see different aspects of the data, and when you put them together, you come up with a reason why the data exists, or you come up with a reason for some phenomena that is supported by the data, right? And we call that a hypothesis or an explanation. This is why the ocean is blue. This is why grass is green. This is why there's mountains. This is why there's volcanics in the middle of the Atlantic. This is why you have the same eye color as your father, etc. So the reason that plate tectonics is a good example of a theory is once data is collected through observation and experimentation, right, and you form a hypothesis, then what you can do is you can test that hypothesis. And through testing, experimentation, and lots of review by your peers, that is the scientific community, if you have a hypothesis that survived repeated challenges, either through experimentation or through peer review, it's accumulated a substantial body of support. So it's supported by other theories, other data, other hypotheses. And it predicts the outcome of new experiments or natural phenomenon. Then you can take a hypothesis and you can elevate it to the status of scientific theory. Okay? So scientific theories are the best possible explanations for natural phenomena based on current research and technology, right? Science is always evolving, always changing as we get new data. I noticed this during the pandemic. A lot of people would say, well, you know, the scientists said this, and then, I'm not trying to get political here, but I'm just saying, people will say, well, the scientists said this, and then they said this, and then they said this, so they don't know what they're talking about. And while that may be true in certain cases, overall, that's exactly what you want science to do. Overall, you want science to have the best possible answer at the time given the data. But as new data emerges, new hypotheses are formed, new hypotheses are tested, and they can be changed, they can be rejected, and this sort of thing. So it's important to know that science is evolving that way. But as different things evolve, along the lines of as you get different data and you modify your hypothesis, scientific theories can change. They don't change very much. This doesn't happen very often because the process by which something becomes a theory is usually tested to death, right, before it becomes a theory, okay? And one thing I want to point out here is that scientific theories are very different than scientific laws, okay? Scientific laws are basically, in a way you can kind of think of it like supported by more, I guess I want to say math, right? It's sort of, think about the laws of thermodynamics, right? Like Newton's laws. So those are observed, but they basically come down to a mathematical equation that's just simply true, right? And it doesn't need to be tested, it doesn't need to be modified. It's kind of set in stone, like the laws of physics. That's very different than a scientific theory. You don't really change scientific law, right? Like the law of the movement of objects, right, in motion. Those are kind of set, right? And they're unchanging. As long as the universe has been around, those laws have been the exact same, down to decimal points, right? As far as that goes. So a scientific theory is not a scientific law, so I want you to remember that. So the theory of plate tectonics, which I said, again, has only been around since about the 60s, can be summarized as the outer layer of the Earth is broken up into rigid plates, okay? So here they are. This is the crust and the lithosphere. And these plates move around on the Earth's surface, and they pull apart. So they move away from each other, like we see here between South America and Africa. This is in the middle of the Atlantic, and there's plates pulling apart there. That's a certain kind of plate boundary that we're going to talk about next week. They can collide, so run into each other. That's like what we have here with the Nazca plate and the South American plate. You see those arrows there. And then we can also get plates that slide past each other, okay? And that's like what we have over on the San Andreas Fault. This is where the plates aren't moving together or pulling apart primarily. Instead, they're sliding past each other sort of horizontally, okay? And for the tectonic plates, they are composed of the lithosphere, so that's the crust, and the rigid, more rigid or more brittle upper mantle. These plates are about 70 in the oceans to about 150 kilometers on the continents in thickness. And the crust is usually continental crust, oceanic crust, or some mixture of the two, okay? And the portion that the crust, so the lithosphere and the crust, the portion that moves over from about 100 kilometers down to about 200 kilometers, you have this portion of the mantle that's very hot, and it's not a liquid per se. It's more like a melted plastic, or you could think of it like really, really cold molasses, the way that moves, although this is not cold. It's very hot. It's definitely not molasses. And this stuff kind of slides around on the top of that asthenosphere, okay? This is sort of the lubricating portion of the outer mantle that allows the plates to slide around and interact with one another at the surface. So the theory of plate tectonics is that there are basically 7 large plates: the Pacific, North and South American plates, the African plate, the Eurasian plate, Indian plate, and the Antarctic. And those are these larger ones here that you see: South American, North American, Eurasian, Australian, African. And then you have lots of smaller plates. There's the Juan de Fuca plate, the Cocos plate, the Nazca plate, the Arabian plate, the Philippine plate. These are the smaller microplates, they call them. Although some microplates are even smaller still than the ones you see in this map. There's actually tons of microplates, maybe. Plate tectonics theorists and structural geologists and stuff argue about this sort of thing all the time. But where these plates are interacting with one another, you get these different types of plate boundaries, okay? So when the plates are spreading apart, we call that a divergent boundary. When the plates are moving together, we call that a convergent boundary. And when they're sliding past each other, we call them a transform boundary. More on that next week. Okay, we're going to do a deep dive on all of these. And they all move relative to one another, okay? So they're all moving relative to the center of the Earth, right? But relative to one another, they're moving in different directions, okay? And we're going to talk extensively in the next section about that. But for the little bit of lab that you're going to do this week that deals with plates, that's really all you need to know is just that there's those plates and that there's boundaries between those plates and that these different types of things are happening at those boundaries. So we're going to have just kind of an introduction in lab this week about that. And one thing I'll close with before we dive into plate motion in the next lecture is they're driven by thermal convection, right? Like that lava lamp with heat moving up and down throughout. And again, like I said, the 3 types are divergent, convergent, and transform. Divergent is moving apart. Convergent, and there are different types of convergent boundaries, are moving together, like converging. And then transform boundaries are when they're sliding past each other. Okay, so we'll leave it at that. Nice 50-minute mark. The last time I recorded this lecture, it was a lot longer than this, and I don't know how I managed to talk so much. So this is a re-recording that's much, much shorter, and you're all luckier for it. So anyway, that'll be that. I'll see you in lab. Email me if you have any questions, or use the link in Blackboard under discussions, the virtual office hours. You can, or virtual classroom, you can ask questions there as though we were in class and you were raising your hand. And that's a public forum so that other people can see your question and see my answers. So rather than email me, it's actually probably better if you have a question about lecture going forward in the class to go ahead and put it in that forum, because then other people can benefit from you having asked the question and me having clarified or answered it. Okay, so I'll see you guys next time. Have a great day.